Security operations centers function in a state of systematic burial. Structured, logical network environments are constantly overwhelmed by an unyielding influx of system data. The core operational bottleneck stems from the parallel deployment of multiple intrusion detection systems. These disparate systems generate a massive, continuous volume of heterogeneous security alerts. This chart shows a stark mathematical reality. A major enterprise SOC processes tens of thousands of raw alerts daily. Even after automated filtering, hundreds of high-priority alerts remain, far exceeding the capacity of manual human investigation, which takes an expert up to 20 minutes per case. The industry standard technique for resolving these alerts is provenance-based backtracking. This technique takes an initial alert, a point of interest, and recursively queries system event logs in reverse. By tracing causal dependencies backward from the alert, an analyst maps the exact sequence of events to identify the initial compromise. When this triage process bottlenecks and alerts are left uninvestigated, the initial access vector remains open. In the 2020 toll group incidents, an unresolved entry point allowed attackers to persist on the network, resulting in a devastating secondary ransomware attack that exfiltrated 200 gigabytes of data. Backtracking assumes a flawless chain of evidence. In production environments, physical realities cause that chain to snap, severing the path of investigation entirely. These broken causal chains occur constantly due to lossy data compression, dropped network logs, and deliberate anti-forensic operations executed by attackers. The physical graph edges simply cease to exist. When traditional systems attempt to bridge these gaps without understanding semantic context, they trigger a dependency explosion. The system indiscriminately pulls in thousands of benign, loosely connected system nodes, rendering the investigation graph illegible. To inject semantic understanding into this process, modern security operations centers deployed a baseline solution, feeding raw security telemetry directly into a general-purpose large language model. The results degrade rapidly. During multi-stage analyses that stretch across thousands of lines of logs, general-purpose models lose their operational context. They succumb to semantic drift and generate plausible-sounding contextual hallucinations rather than accurate forensics. In live production audits, this unguided language model approach yielded an actual verified success rate of only 64.7% as attempted to access a known malicious IP. Working backward from this point of interest, the goal is to locate the specific file execution log that spawned the malicious Python process. The critical execution log linking the file to the process is gone. Environmental data loss has erased the physical connection. Traditional backtracking systems halt immediately. Without strict physical connectivity, their logic cannot bridge the gap to continue the query. Facing this missing log, the unconstrained language model executes a broad, directionless search. It pulls every available log field indiscriminately to find a connection. This untargeted query triggers a massive influx of irrelevant noise, instantly causing a dependency explosion. The sheer volume of returned data floods the language model's effective context window. It loses the investigative thread and fails to identify the source. Bridging physical gaps in the logs requires a system that can leverage semantic logic to infer missing steps without triggering a catastrophic data avalanche. To solve this, the SherAgent architecture removes the language model's ability to write open-ended search queries entirely. This document details SherAgent's primary constraint. The system restricts the model's outputs to predefined causality-guided SQL templates, controlling which entities and activities can be retrieved. By utilizing specific adjustment strategies, the architecture shifts the investigation to highly targeted existence-based querying. The language model analyzes the available evidence and hypothesizes the existence of missing events based on their temporal proximity and expected semantic behavior, systematically testing these hypotheses through the templates. By constraining the search space, the system retrieves only the necessary logical context, explicitly preventing the data overload that crippled the baseline model. The SQL templates operate as rigid guardrails, transforming the unpredictable generative text of an LLM into a highly controlled, deterministic search mechanism. Once the targeted data is retrieved, it must be filtered. Traditional heuristics struggle here because they cannot parse unstructured semantic fields like a process's command line. Given access to the semantic fields, the constrained language model accurately reads the command line execution string. It discovers that a benign markdown file was manually renamed into an executable Python script. By identifying this specific semantic action, the system establishes a logical continuity. It tracks the markdown file back to its creation event, successfully bypassing the missing execution record and bridging the broken causal chain. The final architectural requirement is maintaining this precision across a long-duration investigation to prevent the model from hallucinating conclusions as its memory degrades. SherAgent achieves this by externalizing the investigation state. It stores analytical progress in a dynamic tree structure. The system forces a global audit against this tree. If a new branch cannot prove a logical, causal connection to the active tracing path, it is pruned away. This external framework allows the architecture to continuously reevaluate evidence, cleanly roll back from dead ends without lingering context pollution, and measure its progress against strict success criteria. Decoupling the investigation state from the generative model completely neutralizes semantic drift. The model acts only as a processing unit. The tree dictates the reality of the investigation. The efficacy of these architectural constraints is proven by empirical performance data generated in a live production environment. This chart compares the actual reliability of these systems. The baseline model routinely generated plausible investigation reports that ultimately failed human verification, falsely inflating its success rate. Deployed over months, SherAgent processed 53,849 real-world alerts, maintaining a human-verified success rate consistently above 96%. In the most severe edge cases, attacks suffering from total log omissions regarding the involved entities, SherAgent accurately recovered and resolved 78.3% of the broken causal chains. This accuracy scales efficiently. The architecture completes complex investigations in under 4 minutes, incurring an average API cost of less than 10 cents per run. Automated triage at this scale is impossible using raw intelligence alone. It requires a system that simultaneously enforces logical reasoning and strict structural continuity. The success of the architecture relies on interlocking precision. A chaotic, highly volatile energy source is harnessed to drive a strictly controlled output. A large language model provides immensely powerful semantic reasoning, but it is inherently volatile and easily distracted by noisy data. True automation in cybersecurity requires caging that reasoning within deterministic constraints, relying on rigid SQL templates for data retrieval and strict tree-based state tracking for memory. To reliably scale threat investigation in the wild, the industry must stop treating language models as standalone, omniscient analysts and begin architecting them as highly constrained analytical engines.